Okay, hello guys. Welcome to the last talk of the day, also the last talk of the Defcon 18. Well, I'm Benson and this is Jeremy. We actually are very surprised that you guys are still here. You guys didn't, got passed out from last night, crazy Saturday night. Actually, the talk is about malware analysis. We first will introduce some very famous malware instances that we have collected, and then we will explain how these malware try to fight against anti-malware solutions. And then we propose a method that we call malware runtime forensics, that we try to analyze these forensic data on these malwares. And then we try to do automatic clustering. That helps us to identify who is who after all. So as I have introduced, I'm Benson and then it's Jeremy, and then another speaker, Wayne, actually went back to Santa Clara with our one of our colleagues. He actually got so sick on the last day. So Wayne was not here. First of all, we actually would like to introduce some Chinese characters. Actually, the character on the upper left corner it actually represents the term malicious in Chinese. And then the first malware sample that we're going to introduce here is actually one of the malicious malware that is very famous called Sharpstealer. It actually helps you generate programs that you can steal username and password from these famous common well-known applications such as Internet Explorer, MSN Messengers, or your Firefox. So it's more like a malware generator. The next one is called Bfrost. This one is also very famous. It's a very famous bot malware. As you can see on this CNC console, it actually has 28 users connected back to this CNC console. So there are 28 victims. And then the one you see up here, it's a Chinese version. It actually derived from the Bfrost, and it originally derived from Bfrost by Chinese hackers. And then these characters, if you notice that it's in traditional Chinese rather than simplified Chinese, so got localized by Taiwanese hackers. And then the block you see here, you can specify where is your CNC console, and then whether you want to pack the resulting malware or not. You can also specify if you want to add more plugins such as keyloggers, so on and so forth. So it makes generating a malware that help you steal, that make you infect victims to be a bot very easily. And then the second phrase we're gonna introduce in the talk is called 漏鸡. 漏鸡. This one represents chicken. While in Defcon you see that the wall of sheep, well in Chinese hacker community they don't call it sheep, they call it chicken. So you actually see a form of chicken instead of wall of sheep. And this is the wall, the form of chicken. Yeah, so obviously you know where it came from, right? In the wall of sheep, we only show username and password in Defcon, but in the form of chicken, you get to see victim's face through the webcam. Okay, and then the modern advanced malware are so powerful that they have so many advanced features. These features including anti-blah blah blah features, such as antivirus, going against antivirus, going against your firewall, and then going against your hips. And then it has more features if you are willing to pay more. So if you pay more, you get to enjoy more features that you can put into your malware that you generated. So it's more like a malware as a service in this community. So you can see some features such as, so in addition to antivirus, fighting against antivirus, fighting against firewall, fighting against the heaps, you also have anti-VMware, anti-debugger, anti-API hookings. So these are the features that once you pay more, you can enjoy. So now we will also talk about how they fight against the sandboxing environment, how they can detect whether they are in the sandboxing environment or not. These are the approaches that they use. The first one is how they can detect whether they are inside a VM or emulator environment. Usually, one approach is that they would try to check the base address for these IDT and LDT, because in a normal machine, the IDT and LDT address starts with A something. If it's not starting with this address, then it's probably in a VM environment. And they can also check for the devices, because these devices in the VM environment or emulators, for example, the CPU IDs tends to be very unique. The model name tends to be very unique. They also have a very specific PCI device. So if they check against these special hardware specifications, they can recognize whether they are in the VM environment or emulator. And after all, they can also try to launch these backdoor commands, because these undocumented backdoor commands are only available when you are inside an emulated environment. So it's very easy for malware to recognize whether they are in a VM environment or emulator. And then, in addition to VM emulator detection, they can also check whether they are in a sandboxing Windows environment or not. Because in a sandboxing Windows environment, you tend to have specific service, you tend to have a specific process name. So they can try to check whether these specific process or specific service name are there or not. Also, they can also try to detect these kernel mode SSDT or the user mode API hooking is presented or not. And then after all, the last one is a very trivial one, but works very effectively. They actually have a list of legitimate Windows production ID, because these vendors, they have to have legal license of their Windows. So they have a limited set. And this limited set are being collected by hackers community, so they know whether they are inside the sandbox or not, simply by checking against these legitimate license. So we have introduced how modern malware try to detect whether they are in a sandbox, VM, emulating environment or not. And then what's even more is that they can also try to defeat you, even when you try to have monitors, even when you try to hook, and then try to detect them. So what they can do is that they can restore the SSDT hook. They can also unload the notified routine or process of thread or image or registry. They can also unload this file system filter, restore the SSD hook, unload the TDI filter, which is for networking, and they can also remove these NTFS attached device. So you can see there are a lot of things they can do, try to unhook you, and then try to neutralize your monitors. And then after all, there are also some heaps. They try to implement their protection layer on the file system level. However, these modern malware, they can also try to launch direct root disk access through the disk.sys. Then they can bypass your file system protection. So what we try to propose in our talk is actually a behavior analysis. And then we try to do forensics. There are two approaches for behavior analysis. The one is called a network-based approach, which we'll not address in our talk, because the approach that we take is actually a host-based. So for host-based approach, we already mentioned, you either use a VM, you use a sandbox, but as you already know, malware can defeat these very easily. So what we do is actually use a host-based runtime forensics. So in our runtime forensics, what we did is that we let the malware execute it, and then we try to do forensics after it's already executed. So we collect a snapshot of the environment, and then we try to identify the special features in that environment. And because we already let the malware execute, we don't have to have monitors to see what happened to the malware during its executions. We also don't have to do hookings either through the API or not. So we have nothing for the malware to defeat us. So you might be wondering, so what kind of features do we try to get when we study this snapshot of an environment? There are three aspects of features that we try to collect, we try to analyze. The first one would be the installation remnants. These are the installation files after the malware tried to execute on the system. They either could be startup files, they either could be additional registered keys. We also study the memory layout, try to find some memory block or suspicious DLLs. And then we also try to find if there are suspicious malicious behavior inside the systems. For example, a hidden process, a hidden files. So these are all the symptoms for malicious behavior where a legitimate software would not exhibit on your system normally. And then among the three aspects, we would further explain the one how we study memory layout, because this one is the most hardest one to work with. So how we study the memory layout, first we have to identify which process is suspicious. So the way we identify this one is we first will fetch the process and service list, and then we compare against the list, the process list that is already inside the system. And we find a difference between these two lists. And then how we fetch the process, including we scan all the following tables, as you can see up here on the slides. And then by doing this, we already identify the hidden process. We already identify the process that is very suspicious. Then we have to further dig into, we have to find which part of this process has the suspicious DLLs. So we will fetch the DLLs from the LDR, and then we analyze the memory layout, also its structures, scan the code block, try to find the code blocks that is which we'll explain later, how we do this part to find the suspicious DLL. So what you see on the graph, normally a process will involve a lot of DLLs where they are implicitly linked. But if there is a DLL that is explicitly linked, it's very likely that it's a suspicious DLL. And that is how we identify a suspicious DLL. So that's what we call, we check the LDR, and then we scan the import table, try to find the suspicious DLL. On the other hand, if the process actually does not load a DLL at runtime, it actually do some code injection instead. Then our approach is that we will search the memory, try to find the suspicious P image. So in this flowchart, you can see that, so let's review. We try to identify suspicious process, and then we try to identify suspicious DLL. And then inside this suspicious DLL, we do our runtime forensics, which includes LDR scan, PE packet signature check-in, code disassembly, string extraction, and then file inspection for hidden files. So these are the action items that we do for runtime forensics once we already identify the suspicious memory layout. And then in the following slides, we will introduce some examples that we have collected in the wild that use all these kind of anti-malware techniques. The first one would be the Bifrost. You already seen in the previous slides. This one is a very famous bot that being used in Chinese hacker community. And its Chinese name is called Rainbow Bridge. And the phrase is actually from its icon being used. So you can see the icon is a rainbow bridge. So that's its Chinese name. And this Bifrost, it uses code injection. So it's not DL injection, it uses code injection. So the only way you can find this suspicious code injection, you have to scan the memory and then try to find the P image. And then you will notice that it tried to do code injection into the IE browser, and then it will access a series of URLs. And the first one, if you notice that the first one it tried to access is Microsoft.com. It actually tried to check if the network connectivity is available or not. And then it tried to access some CNC servers. These CNC servers are actually named after Chinese vocabularies. For example, the one that we highlighted is actually called may I know, you ask a question, may I know, the phrase is called 请问, may I know? Case number 2 is also a very famous one in Chinese hacker community. It's called GhostNet. The original official report is actually released by Canadian researchers, Shadows in the Cloud. And then from the sample, you can see that it tried to install itself as a system DLL file into the system. And then it will connect to a CNC server. When we try to reverse these binary, we also identify the botnet commands that it can use. So you see all these botnet commands that this GhostNet can use. Notice that this GhostNet has nothing to do with the GhostRat malware. And then the string at the bottom, it's how we find out its original project name on that malware author's computer. It's actually called CXP. So it's the original project name before this malware being compiled. Okay. And the URL that we mark is actually one of the CNC servers that this malware sample tried to connect to. And this CNC server is also being mentioned in the Shadow in the Cloud report. The case number 3 is DFN666.net samples that we collected a few months ago through the mass SQL injection attack that have been launched recently, starting March. And these massive SQL injection attack, these malware will use shell execute a hook, meaning that it will affect your explorer, so that once you get infected, it will try to connect to all these online games and then try to steal your username and password for these online games. We have a very detailed story about this massive SQL injection on our blog. And this one is still ongoing nowadays. So even though its first experience are back in March, and it's still ongoing. So the last one would be the Zeus bot. It's also another malware that we study. And this one is a very famous one as well. You can see that it's actually trying to use the winlogon notify, so through the regis key, and then it will infect every process you have on the system, and then it will connect to a CNC server. Then you will become a bot. The Zeus bot is so famous that it even has its wiki page, and one of the security vendors even named it called the king of bots. Its botnet size is kind of like a 3.6 millions. So now we will go into how we do malware clustering, because we already know so much about malware, and then we know how to study them, we know how to do forensics on them, we know all their techniques. Then how do we do clustering? And then you might ask, why do you have to do clustering? You already know it's a malware. So the reason behind this is very obvious. Then you can group those that are alike together. So the way we do malware clustering is we try to compute the similarity between these malware instances. And so our final result, we will have to come up with a similarity matrix, which is a score that indicates how similar any two instances are compared between each other. So we will build a similarity matrix of the malware samples that we collected. So among the test sets that we have, it's more than 400 malware samples. We do forensic reports on all these malware samples. And then we try to extract the 3 significant features that we just mentioned: installation environments, memory layout, and suspicious malware behaviors. And then all these features, they will have a score. They will have a score. And then for every malware that have this score, it will compare against another malware instance. And then you can get a similarity. And then we compare with every malware instance. You get a vector of similarities. And then finally, you get a matrix of similarities. And this is how we come up with the matrix after all. And then we automate this process through our tool called ZeroBox. So ZeroBox will scan all the malware samples that we have, make it execute, and then study it, get a report, and then come up with the matrix, and then do the clustering. And then you will be able to group into different groups. In our test samples, we actually have 408 malware samples that we collected on the 8th of July this year. Because we have a product called Hack Alert that can scan websites for Trojans that are already on that website, and then we collect all these malware samples. And then we also test against these malware samples on some existing antivirus, and the hit rate is not that really good. Some vendors have less than 20%, some vendors can have 50%. So these malware are really new. And how we do the clustering is through the k-means clustering. But we will not get into too much details on why we choose this one. But the clustering mechanism we use is k-means clustering. And you see the similarity matrix, and you see a lot of colors. The reason that it has a lot of colors is because we model these scores into RGBs, because we want to visualize it. Humans has more feelings with visual pictures, so we try to visualize it. And then if you look at the first block, you see some patterns that are alike. Maybe you don't, but we will get into that. So this is the first block. Okay, did you see any color patterns? Definitely you see a lot of color patterns, but actually there are some blocks that differentiate from other blocks. So for example, if you look at the second line, you see the upper corner, there's some gray colors, and then you see it becomes a little pink over the skin color, and then it becomes more purple, and then becomes more like a pale white again. So it seems that you can see 4 blocks within this big block. Okay, so simply by visualizing it, you already can group these colors into 4 blocks. I hope that you guys are not feeling dizzy. Okay. Yeah, and actually every line, as we mentioned, it's a similarity vector. How these malware instances compare against other malware instances. So every line represents a malware instance. And then we use the antivirus to double check whether it's a malware or not. And you can see all these malware different namings used by these antivirus vendors. And then all these malware instances happen to be the same malware family called ZBot, ZooSpot. So even for the first upper block, it's all ZBot. And then even the second block, it's all ZBot. So a total of all these 26, these are all ZBot instances. And because there are some ZBot variants, instead of only believing in these antivirus, we actually try to do manual inspection by our own. We try to double check these are really ZBot malware instance, and then we try to find their versions so that we can tell which variants they are. And there are actually some different bot command in these different ZBot binaries, so you can tell their different versions. So for version 1, it has these commands. For version 2, it has another set of commands. So after our manual inspection, we are able to identify different ZBot variants. So the upper 3 blocks all belongs to version 2 ZBots, and then the one on the bottom are actually ZBot version 1. So based on our experimental results, you see that out of 408 malware instances, we manually identify there are 52 ZBot malware instances. And then among these 52 malware instances, ZBot malware instances, they can be clustered into 4 groups. One group is V1 variant, and then 3 groups are V2 variants. When we compare these clustering results against antivirus results, they actually match with each other. So our malware clustering have the same accuracy as the antivirus. While these antivirus tools, they are only able to identify 26 of them, while we can automatically cluster the all 52 instances. So even though we don't have signatures, because we know how to cluster them, their colors tend to be similar. Then we are able to say that, okay, these malware binary are actually a ZBot family. And then in that big block, we only look at the first block, right? So there are other blocks in that pictures. There are also other malware families, including the Undo families and also the Bagel families, also a very famous malware. So these malware instances, they also tend to be very similar. They have the same color patterns. So the conclusion is that, as you can see, the traditional hooking-based monitor approach already cannot handle the modern advanced malwares, because these modern advanced malwares, they know how to do a lot of anti-malware techniques, including a lot of techniques we mentioned in previous slides. So instead, our approach is to do forensics after the malware already has been executed. So we only need a snapshot of the environment. And the experimental results also justify that because of our runtime forensics, we are able to collect a lot of significant features. These significant features help us to do automatic clustering of malware. So it also helps us to identify even unknown malwares, because we are able to cluster them into the groups that they are more alike with. So that will end our talk. And if you have any questions, you actually can also write emails to us.
With that environment, you run was it a standard desktop PC? Did you try and emulate what would be a normal PC running the normal version of Windows, or did you have a special rig that you had to run this on for post-analysis?
Yeah, so surprisingly, actually a normal PC. Yeah.
But and is it something that, this is a production PC that has whatever software load on it, and you can just load your toolkit on after you infect it with malware?
Yes.
And how long does it take to do that type of, and presumably it connects to your backend, it collects its evidence and sends it out to your backend for
Yeah.
processing?
On average, we try to limit that into less than 30 minutes. Yeah, he'd actually asked whether we use a normal PC or not, or an emulated environment. Our answer is that we use a regular PC, because as we mentioned, there are so many anti-VM, anti-emulator techniques malware can use. And normally, for us to restore all these regular PC boot up until we finish all these forensics, it takes less than 30 minutes. Yeah. Yeah, so we take in a snapshot. After the malware already executed, we try to execute our binary. So we try to launch our program.
How do you get the difference? What was the state of the machine first and after the malware?
So then after we launch our program, we will look for all those three significant features we mentioned. So we study these startup keys, all these installation files, all these memory layouts, and all these suspicious behaviors. Yeah? It's still on a very early stage of prototype, yeah. And we try to make it more mature so that we can release to the community. Yes?
Since you're running analysis on physical machines,
Yeah.
are you guaranteeing the state once you start with your next scan?
And then that's why we have to restore it. Yeah. Yes?
Are you concerned about malware authors trying to circumvent your programs, executing the same way that they do the VM?
Yeah, it's possible. This is why all these kind of forensic tools, they have to stay anonymous so that they cannot become one of the blacklist. Yeah, once you make it into a product, then they will try to stop you right away when you try to install it. Yes?
Have you looked at taking your malware samples, your border samples, and also running legitimate applications and seeing if your clustering is able to determine legitimacy versus malicious?
Yes, definitely, yeah.
You did look at that?
Yes. Yes. Yeah, we will try to make it public because we are still in a rush to finalizing it. Okay, thank you very much. And then if you have any feedbacks, we welcome you to write us. Thank you. See you Defcon 19.